So in biostatistics for biomedical students, biochemistry student researchers and all that, at advanced level, maybe grad level and all that, you are going to encounter questions under probability functions like binomial distribution, Poisson distribution and all that. So I have given us two typical questions that are under this function. So if you have a question like this question number 1, you have two parents each have the gene of cystic fibrosis. For each of their children, the probability of developing cystic is 1/4. If there are 4 children, find the probability that exactly 2 will develop cystic fibrosis. Fine. Now, in this case now, you are going to use a probability function that is under the binomial distribution. So here, we are solving question 1 now. So solution 1, the formula for this is generally P. Let's deal with this one first. So this one can multiply this now. We say 6 times 0.0625. This gives us 0.375 bracket 0.75 square 0.75 square. This gives us 0.5625. Here, you multiply both together now, times 0.375. This gives us 0.211 approximately. So, which you can also express as 21%. So that if you multiply this by you multiply it by 100, you want to convert it to percentage. You want to know the percentage here, because sometimes the answer may not be in this unit. It may be in fraction form, it may be in decimal, it may be in percentage. So whatever you want, you can just convert it accordingly, and you write your answer down. You'll be able to check your answer. So this one will be 21% approximately. So this is a function of it. So please, let's look at the formula again. So the formula for this distribution is P, S equal to S, N of S, then P. Then you get your parameters given this way. Then you slot in the parameters, then you get your answer. So this is how this one is solved. Now quickly, let's look at the question 2 now. So for question 2, now if you see the question is the WBC, that is white blood cell count of a healthy individual can be as much as 6,000 per cubic millimeter of blood. That is a drop. The probability of a white blood cell deficiency per cubic millimeter of blood is 0.01. If a blood drop is taken from an individual, then what is the probability that 1, no deficient white blood cell, the other probability is 1 deficient white blood cell, and 3 at least 2 deficient white blood cells. So quickly, now what you first of all do now, you identify this as, because you will not be told that this one is a Poisson, this one is not this one is a Poisson distribution, or this one is a binomial distribution. You are the one that will identify it, so that you know the kind of formula to use. So what are we going to be looking out for? We look out for the what do you call it now? The average value here that is given to us as the probability value as 0.1. Then the what do you call it? The population, the total overall population is very high. So if it's very high, then you are going to use a Poisson distribution. So this probability is very high. So compared to this one that is just 4 and all that. So this one, this high value, anytime you are seeing high value, this gives you the information that you are going to use a Poisson. So just take anything 1,500, 6,000, all those big values like that, you can't use a binomial. You are going to use what do you call it, Poisson distribution. So in Poisson distribution, P of S equal to S is given as lambda S, then lambda S, then we have E minus lambda over S factorial. So this is a formula for getting the Poisson. This is a Poisson formula. Where this E, the E is a constant of 2.6 0.7183. So this is a constant which you must know. So this one is a constant, then you have lambda. So then lambda itself is gotten from NP. That is a formula, you get it from NP. So what is NP? NP is the population, the total population, which is 6,000. 6,000, N is 6,000 times the P, which is the probability, 0.01. So 0.001. So that is the probability. So meaning that our lambda here now is 6,000 times 0.001. This gives us 6. So lambda is 6. Then, now that we've gotten this, the other value we need to get is our S. So the S here is that no deficient, that is the average we want to be getting, no deficient white blood cells. So S in this instance, S will be 0 because no deficient white blood cells. So we compute this value into this. So what do we have? We say P bracket S, when S is equal to 0, S is equal to 0 is equal to, so if it's equal to this, then the lambda, which is 6, raised to power S, which is 0, then E, okay, our E now, let's just substitute directly. E is 2.7183, then raised to power minus lambda. So minus lambda is minus 6, so minus 6 over S factorial. What is our S? It's 0, so 0 factorial. So this is it. So 6 raised to power 0, 6 raised to power 0, 6 raised to power 0 is 1, then times this one raised to power minus 6, that is 2.7183 raised to power minus 6 is equal to 0.002479 over 0 factorial. 0 factorial is equal to 1. So this is 1 times this, it gives us 0.002479. So if you approximate this, you can convert it to percentage by multiplying it with 100. In case your answer is in percentage, so you get it this way, say 2479 times 100. So this will give us a 0. So you write your answer like this, or you say or 0.24 or 25%. 0.25%. So this is that. Then the second option says one deficient white blood cell. So what this simply means is that P here, S is equal to 1. One deficient white blood cell. So what you still do is to recall this formula. Here you have the lambda. Lambda is 6 raised to power 1. Instead of writing S now, you put 1. Then times E is 2.7183, which is a constant, raised to power minus 6. So our lambda is 6 minus 6 over 1 factorial. So when we compute this now, we have this as 6 raised to power 6 raised to power 1 is still 6. So times this 2.7183 raised to power 6 minus 6 rather, minus 6 is equal to, we've done that calculation before, so that will give us times 0.02479 over 1. So if we compute this further, this becomes 6 times 0.02475 is equal to 0. So this gives us 0.1485. So that is divided by 1 is still the same value. So in percentage now, that gives us 14.8%. So Then you do the same thing. Okay, this one is at least 2. So quickly, let me quickly solve this at least 2. At least 2 is a problematic one because here you have to use the equality function now. So let's quickly look at the last part, which is the last part says at least 2 deficient white blood cells. So if it's at least 2, at least anytime you get the word at least, the what should come to your mind is greater than. So meaning that S is greater than or equal to 2. That is what the at least 2 means. So then your lambda remains the same, lambda S from the formula, then E minus lambda over S factorial. So here now, because it's less than 2, another function, in order for you to calculate easily, greater or S greater or equal to 2, another way you can easily calculate this is to say P S greater or equal to 2 is the same thing as 1 minus the probability of S less than 2. So this is a way to simplify it. Instead of calculating it up to, because the number is very large, you can't calculate up to those numbers. So just do the 1 minus the P and say S is now less than 2. So with that, we'll be able to quickly summarize it. So what this now means is we now have the probability as 1 minus the probability of this one, which is now lambda 6S. So we are not counting from less than 2, 0 and 1. So 0 and 1 is what we are calculating for. And remember that we've already calculated for 0 and we've calculated for 1 before. So it's easy for us to substitute our value now. So it means instead of saying the value for this, okay, let me just write the value here. So 6 will be 6 raised to power 0, then times 2.7183 minus 6 over, assuming you're having different values, so it's better you just show it this way. So we now have 0 factorial, then plus, we have a square bracket this way. We now say 6, 1, this one is 1, 2.7183 minus 6 over 1 factorial. So we say less than, remember something is less than 2, so it's not up to 2 this time now. So 0 and 1 are the only numbers that are less than 2, so we stop at this value. But remember that we've already solved for it from the source, from the previous solution. So what we just do is you are allowed to import this now. We just bring this one forward, this value. So we bring this value of 0.002479 plus that of the one. That of the one is 0.14. So because we solve for it, there's no point solving it again. So we say 1 minus, so we add these values together now. So we say 0.002479, we're almost done. So plus 0.1485. This gives us 0.150979. So now this old value subtracted from 1. So we now subtract this from 1. So if we subtract it from 1, that would be 1 minus 0.150979. This gives us 0.849021. So approximately 0.85, which, or you write this, like I said, you can give it a percentage in your answers. So this becomes 85%. So if you multiply it by 100, so you have it this way. So this is how to solve the probability, under the binomial distribution and the Poisson distribution. So thank you. Like, share, and subscribe to our channel. Thank you.